connected abroad. So welcome to welcome all to FSE 2022 in Athens. So I'm very glad to be here and that you're all here to present for this conference, because as you know, this conference has a kind of long history, so probably not all of you are aware. So originally, FSE in Athens was planned to take place in March 2020. So this basically means that the banquet place, so the venue place and everything was already booked in 2018. So then some kind of set lanyards and already like bought in 2019. That's why you have a 2020 logo actually on your lanyards. And then even we opened the registration, and actually some people registered and had a lot of participants until February. And then you can all know what happened, right? So we had to cancel the event, but we said, okay, summer will arrive. The virus does not survive to hot temperatures, especially Athens temperatures. So we will just wait it to die. And then we have FSE again in November. So that was the plan. So we were thinking opening the registration, and then you also know what happened. So second wave. So we had to cancel it again. We had it in hybrid mode. And then we kind of gained wisdom and said, okay, we will wait to see what happens, and we'll try again in March 2022. So we are here today. And of course, this conference would not have been possible without the hard work of the program chairs and editors of TASK. So I would like to thank Itai Dinur, Gaetan Laurent, and Mark Manning for their very good job that permitted us to have today at this FSE 57 papers, very good quality to be presented into 10 different sessions. So we also have two very nice invited talks. So a talk by R. Dunkelman on Tuesday, and another one by Christian Reichenberger on Thursday. Okay, I will present you a little bit the numbers of the participation. So first I will start for all the people that are abroad, that were not able to come physically to FSE and are registered to us online. So we have in total 112 participants, so mostly regular, but also some students. And they're coming from 29 countries. And as it's not surprising, but you can see that Asian countries, particularly China and Japan, are the countries with the highest number of attendees. So considering the on-site, so you'll see that the room is kind of it's not empty at all. There are a lot of people here. So we have in total 76 participants from 17 different countries, and actually also some countries out of Europe. That is quite surprising, and we're very happy about this. So you can see that the France delegation is the biggest one. So I would like especially to thank them. Without them, the room would be much emptier. So they have their proper logo for this. Of course, we have to thank our sponsors. So one silver sponsor, the TII, and 3 normal sponsors that helped a lot to take some of the expenses. And now will come some practical information for people who are on site. So if you're not living in this hotel and you want to connect, so you can use this public Wi-Fi, Royal Olympic. Then there is a password, a Royal with big, all written like this. And you choose to log in as non-resident. And then normally this should work. Important information concerning food. So we will have some coffee breaks and lunches. So all coffee breaks will be taken inside this room. So the old people that will bring the coffee just in the back of the room. And lunches will all be taken on the 7th floor, same place as reception yesterday, to the restaurant part. So basically they're all at the same time, 12:45, except of Wednesday. Okay, Wednesday it's a little bit half an hour later. So we will also have a conference dinner. The conference dinner will take place on Thursday at 7:30 local time. It will be held in the Dionysos Zonas restaurant. So it's a restaurant in walking distance from here. So you can see here, and it's basically like 15 minutes to walk there. So we can otherwise go all together, or you can go by your own. The important is to be there for 7:30. Yes. Sorry? Oh, because you don't see me. Okay. Okay. Thanks. So we have also a small social event. The social event will be a visit of a guided visit of the Museum of Ancient Greek Technology. This will take place on Wednesday afternoon. And since the museum is quite small, we can go there. We cannot go there all together. So there will be 3 groups. One group from 3 to 4, another one 4 to 5, and the last one from 5 to 6 local time. And to know which group you are in, just look at your badge. And you have a small color. So pink color, it means the first group, then green color, second group, and blue color, it's the third group. Please do not, you can change if you want groups between them, but the number has to be constant, that you can basically exchange with someone else, but not decide by your own to go to a different group, because we don't have to be more than 30 for each visit. So if you have some funny or interesting on break or like the results you want to make them know, there will be a RAM session for this, and Christophe Baerle and Léo Perrin will be the RAM session chairs. So the information for submission is already on the FSE website, so you can go there. The server is open if you want to submit your proposal, and so the deadline is tomorrow at 9 p.m. Athens time, and you have also here the UTC time. So remote participants are invited to submit also their presentations. So Christophe and Leo, let me know that there will be some prizes. So as we are in Greece, the prizes will have Greek names. So you have the Aristophanes prize for the funniest talk, the Electra prize for the most tragic performance, and the Odysseus prize, not for the longest talk, right? But the one with the most mythological references. So if you want more questions, you can ask to Christophe and Leo. Just a small information about the registration. Yesterday, you got some small bottles. So what are these bottles? So basically inside there is a sweet liquor that's only produced in Greece, in particular in an island of Greece that's called Chios. So what you got inside, it is based on a resin that comes from a tree, that this tree is only planted on this island, Chios. And these bottles were ordered like in 2020, so they're waiting for you since this. So please drink them at your own risk. It should be okay, but well, I don't want to have the responsibility for this. Okay, so for physical performances, if you're presenting, please come and put your slides with a USB to the conference computer. It's not possible to use your own computer because we have everything, the sound, everything that goes from here. If you don't have a USB stick, you can also send your emails to this address, but please do this not the last minute because it will be complicated. So do not speak too close to the microphone. It's not true anymore. You can speak because the sound is not that high, and of course be on time for your session. Another problem we have, at least for today, is that we don't have a sound. If you speak from the audience, we cannot hear you. So that means that if you are talking and you have a question, please repeat it so people on Zoom can hear it. We hope to resolve this problem for tomorrow, but for today, it's the best we can do. Okay, for remote attendance, some just guidelines. So of course you can follow the conference or Zoom if you're registered, or otherwise on YouTube. You can ask your questions on Zulip, and we have for every session, we have also a remote chair that so do you hear me from Zoom?
Yes.
Okay, so you also, okay, great. So you can have a remote chair that will take their questions on Zulip and take care of them. So please use your real name in Zoom follow the SCR code of contact, and of course, mute your microphone where you're not speaking. Please be there also on time meaning 10 to 15 minutes before the beginning of your session. And if you have any problem of virtual nature, please send an email to Kevin and Kay through this address. So basically, that's all I wanted to say. I would like to thank all of the people that made this conference possible, and there are a lot of them. First, of course, the program chairs that without them would not have any paper to present. Kevin and Kay that do a really great job to help us with all the virtual conferences. Brian and Douglas that help us with all of the practical, financial stuff, and then really do a very good job. And of course, the FSE steering committee, the SVR emergency committee, and all the session moderators for this conference, all PhD students, particularly from Versailles, that helped yesterday with registration and will help with all the sessions. And of course, all of you authors, speakers, and attendees to be here. So I think Itai would like to say some words on the program.
Thank you very much, Christina. So first of all, it's very nice to see you after all this time. So yeah, I'm very happy to be here and to see you. And let me say just a few more words about the program. So Christina basically already said most of it. I'll first repeat a few things. So we have altogether 57 papers to be presented in 10 technical sessions. The first session will be the next session, the award paper session, and then we will have 9 additional technical sessions. And in addition to the technical sessions, we have 3 so-called special sessions. So we have 2 invited talks. The first invited talk will be given tomorrow on by Ordunkoman, and the second will be given on Thursday by Christian Rechberger. And we will also, of course, have a RAM session on Wednesday, as Christina mentioned. And besides that, so in the afternoons, we will have an in-person workshop. So this will be a workshop that is basically will not be live streamed or recorded. So it will be, as I said, just for the local attendees. And the goal of this workshop is basically to allow students to present the work from the last 2 years and in a convenient and a comfortable manner, of course, in person. And by doing this, we hope to be able to fill kind of a gap that was open in the last 2 years by the pandemic. And yeah, so I hope it will be a very good opportunity for the students, to kind of see how a standard conference looked like 2 years ago for those who did not have the experience. And yeah, basically, I think that's all I wanted to say. And yes, I think we can start with the first session. That would be the award paper session.
Didn't this one work?
Patrick, on va juste mettre les slides. Ok, ça va. Ça marche pas. Oui. I don't, Bart, I don't see. That's oh, it's not
It should be there.
Yeah, I don't see it.
Turn this one off for a moment.
Yeah.
You have muted yourself, Christina.
We have to put some slides on. So like slides are missing. So, or just would you send it by email to me finally? We don't see them on the USB stick, so that's.
Yeah, send them to me. If you can go to.
No, because you have to put it here. You just have to send it to me.
Hmm?
Yeah, yes, it's better.
You are muted.
So welcome to the first technical session of this FSE. So it's a special session. We will have all the papers that received the Best Paper Award. And so we have 3 papers that will be presented. And so the first one is by Stéphanie Delon, Patrick Derbès, and Mathieu Bavry. It's called Coaching the Fastest Boomerangs and its Application to Skinny. So first, congratulations for your best paper. And I'll let you present the results.
Thank you very much for the introduction. Okay. So I don't know, can I make the talk in French? Since so many people are French here. Okay, so let's go. So this talk is about something. Christina? Je sais pas comment ça marche.
No, this one didn't work the last. Oh, okay.
Okay, now.
Okay. I don't know why if we need to.
Yeah.
Okay. Well, I don't know if it's already full screen.
I think it's okay.
Okay,
No?
we don't. Okay.
Okay, so this work is about the boomerang distinguishers, which were introduced by Wagner in 1999. And the main idea is to combine 2 short differentials, as it may lead to a better probability than using only 1 long differential characteristic. To compute the probability of the corresponding boomerang, we used to use an independence assumption. And unfortunately, this assumption does not hold in practice. Indeed, we found several examples of non-returning boomerangs. And the problems occur at the junction of both the lower and the upper trace. So there were some attempts to refine the probability of boomerangs, for instance, the ladder switch or the sandwich. But in 2018, Carlos Cid and his co-authors introduced the boomerang connectivity table, BCT, which is mainly a unified view of all the previous works, and which is a pre-computation of all the possible boomerangs through one single S-box. So you have the formula of the BCT right here. So it's very close to how we compute the DDT, for instance, for one S-box. So originally, to search for the best boomerang distinguishers against one given cipher, the idea was to first search for the best differential characteristics on R1 rounds, to search for the best differential characteristic on R2 rounds, and to combine them to obtain an optimal boomerang characteristic on R1 plus R2 rounds. And we were able to compute its probability like this. So this process was optimal, okay, because if you improve the probability of one of the differential characteristics, you will improve the probability of the corresponding boomerang. But now we know we have to refine the probability of the boomerang, mainly because of the middle rounds. And actually, the process didn't change so much. So we are still searching for best differential characteristics. We combine them, and we just refine the probability of the corresponding boomerang. The problem is that this process is not optimal anymore, okay? Because it is not true that the best differential characteristics will lead to the best boomerang distinguishers. So that was the starting point of our work. And our idea was to directly search for boomerang without searching for differential characteristics. So what we proposed was to use a three-step approach to search for the best possible boomerangs against a block cipher. So first, we propose a MILP model to search for truncated boomerang distinguishers. Then we use a CP model, so a constraint programming model, to search for the best instantiations of the previously found truncated boomerang characteristics. So if we combine both the first and the second steps, we obtain an algorithm to search for the best boomerang characteristics against a block cipher. And then we added a third step to evaluate more precisely the probability of boomerang distinguishers by computing cluster of boomerang characteristics. So this work was applied to the block cipher Skinny, but it is highly adaptable to many other ciphers. So why Skinny? First, Skinny is a very simple, easy to understand block cipher, and all of its internal components are very easy to modelize. So for instance, the mixed column matrix is a binary matrix, which simplifies a lot the MILP modelization. Similarly, the Twiki schedule is linear, which also simplifies all the models. And the DDT of the Skinny S boxes are very interesting regarding differential cryptanalysis techniques because they contain a lot of different values. Okay, so searching for the best differential characteristics against Skinny is very interesting. So it's the same for boomerang characteristics. So here are the results we found for the block cipher Skinny in all the different versions. So as you can see, we found a lot of new boomerang distinguishers in a lot of settings. And in particular, we did improve all the previous results against this block cipher. And the most interesting result is probably this one, because for 18 rounds of Skinny 128 in the TK2 setting, we did improve the probability of the best boomerang distinguisher by a factor 2 to the 30. So that's all the results we found with our approach. So how we did that? So first, to search for the best boomerang distinguishers, we need to be able to compute precisely the probability of such things. And to do that, we need many differential tables, and the BCT is not enough, all right? So we had to use 3 more tables, the UBCT for upper BCT, the LBCT for lower BCT, and the EBCT for extended BCT. So they are all particular cases of boomerangs through one single S box, and they all correspond to one particular case about which differences are set to specific values and which differences are lead-free, R-free. Okay, so the UBCT and LBCT were already introduced in some previous works. They are also known as BDT and BDT primes, while the EBCT was also introduced in a previous work by Mini et al. About Festel, boomerangs against Festel cipher, and it was introduced as a future work. So that's what we did. So now, given, for instance, a boomerang characteristics, like this example here, it's very easy to compute its probability using all those previously introduced tables, and also including the DDT, which I did not mention. So to compute the probability of a boomerang characteristics, all we need is to know which differences are set to specific values, which differences are set to 0, and which differences are free. So for instance, if we look at this particular S-box for both the lower and the upper trail, so here it's the upper trail and here it's the lower trail. In this particular case, for the upper trail, both the differences at the input and output of the S-box are set to specific values, while for the lower trail, they are set to 0. And so in this case, the table to use to compute the probability is DDT. It's only DDT D2. So we only have to compute the probability of the transition D to 2 through one S-box. But if, for instance, we look at this particular S-box through the two trails, in that case, we also set to specific values both the input and the output of the S-box on the upper trail, but also the difference at the input of the S-box in the lower trail. So in this case, it's the UBCT table, which has to be used to compute the probability of this particular part of the boomerang characteristic. So what is very important here is that knowing which differential table has to be used in the computation of the probability only depends on two specific values. So it depends on which differences, if a differences is set to a specific value or not. And it also depends, in the case that the difference is set to a specific values, whether it is 0 or not 0. Okay. And so it allowed us to propose a MILP model to search for truncated boomerang characteristics. So the idea is to start from a MILP model to search for differential characteristics, for truncated differential characteristics on the block cipher. Okay, we have many such MILP model for many ciphers. And for such model, we typically have variables that tell us whether a variable is active or inactive. And what we did was to use, what we propose is to use twice such a MILP model, one for the lower trail and one for the upper trail, and to add extra variables into this model to know whether differences are set to specific values or if they are lead-free. Okay. And so, of course, we had some extra constraints about controlled variables and the relations between active and controlled variables. We also had extra constraints related to tables to know which tables are involved in the computation of the probability of a truncated boomerang characteristics. And otherwise, it works exactly as when we search for truncated differential characteristics. So in truncated differential characteristics, we will count the number of active S-boxes. And here, it's exactly the same, but we will count the number of DDT, of BCT, of EBCT, and so on. And the objective function of the model is only a weight and sum of this number of tables which appear in the computation of the probability. Okay, and it's weighted by the maximum probability of each of those tables. One of the main advantages of this model is that we don't have to introduce any middle round for the boomerang. Okay, because there are some attempts to search for boomerang by dividing the cipher in 3 parts and to search for an optimal differential characteristics in both in 2 parts, and to add some BCT in the middle round. But here there is no need to define any middle round. And actually, our model automatically switches to differential characteristics, to the search of truncated differential characteristics. It means that after, if you run it for enough rounds, it will automatically tell you that the best boomerang characteristics, truncated boomerang characteristics for this number of rounds is to set 1 trail. So let's say the lower trail to only 0, so no difference in the lower trail, and only differences in the upper trail, which it's completely equivalent to searching for truncated differential characteristics. So that's our MILP model to search for truncated boomerang characteristics. So we applied it to the block cipher skinny, but we did not apply it directly. So before that, we made some simplifications. So we noticed that the maximum probability exponent of many tables, like the DDT, UBCT, etc., were the same. So we group all of them into 1 table, which simplifies a bit the constraints. And we also use the Quinn-McCuskey algorithm to reduce the number of inequalities of our model. And at the end, we obtain this table, okay, which counts counts the number of active S boxes, but like the number of BCT, DDT, and so on. And for instance, how to read it. So if we take this 40 here, it means that for 24 rounds of skinny in the TK3 model, the best boomerang characteristics have probabilities at most 2 to the minus 80. Okay. So it's very similar to truncated differential characteristics, to counting the number of active S boxes. And if you look at the SK line, you will see that some of those values are exactly the same as the one given by skinny designers on the website, and for the number of active S boxes for truncated differential characteristics. So now that we have many good truncated boomerang characteristics, the goal is to instantiate them and to find the best possible instantiations. To do that, we use the constraint programming model, highly inspired from another works we made with other authors, which were published at ACNS 21, in which we found that a constraint programming model was much better than MILP model to instantiate differential characteristics, truncated differential characteristics. So we used essentially the same model to instantiate boomerangs. And why it is much faster than MILP, I think it's because the DDT is highly nonlinear. And if you want to describe it using only linear inequalities, it's very hard. It leads to an inefficient model. While for constraint programming model, you can directly add constraint table. Okay, so basically for some variables, you will directly tell the model that all those tuples are possible and the other ones are forbidden. Okay, so that's but the model is very easy. And So we ran this model against many of our truncated boomerang characteristics, and so we were able to find the best possible instantiations of all of them. And actually, the model was efficient enough so that we run it. Trop de temps? Oh, okay. So it was very fast. So we were able to use it to start looking for clusters. So basically, we first search for all the optimal boomerang characteristics, and then we search for similar for other boomerang characteristics with the same difference at the input, output, and the key. Okay, so we start clustering, and for the best cluster, at least the beginning of clusters we found, we performed the precise cluster analysis to study precisely the probability of the corresponding boomerang distinguisher. And so basically, from a boomerang distinguisher characteristics, you can erase all intermediate differences and replace them by all the variables that will be involved if you want to compute the probability of the boomerang distinguisher. Unfortunately, this probability is very hard to compute. Okay, there are a lot of internal variables, so it's very hard to compute directly. So we first propose a new algorithm to reorder the formula, so to have the depth of the formula as low as possible. But it was not always enough, and we had to manually approximate the formula in many cases. So here are the results, and some of the results were practical. So we experimentally verified the probability of several of them. So as you can see, for here, for 3 of them, it's very close. The actual probability is very close to the expected probability, but sometimes there are a gap between the probabilities, and we believe this is because we only consider the case where both sides of the boomerangs follow the same differential characteristics, while they only have to follow the same differential. So to conclude, in this work, we propose a new MILP-CP ad hoc approach to search for boomerang distinguishers. We found many new results against the block cipher Skinny, but there are still some open questions related to this work. So first, our MILP model generates a lot of redundant solutions, so solutions that will lead to the same boomerang distinguishers. As I said, we assume that each boomerang follows the same differential characteristics on both sides, and we still have to add some approximations in the computations of the probability. So the source code of all what we did is available at this address, and there are also a PDF with all the figures of all the boomerangs we claim in the paper. And feel free to send me an email if you have troubles making the code work. I don't know. Okay, thank you for your attention.
Thanks a lot, Patrick. So are there any questions first in the room?
Hi, thank you for this very enlightening talk. It was really interesting. Have you tried to generate the MILP model for 8-bit based ciphers or other SPN ciphers?
I'll just repeat your question for some people. So the question was if they tried generate the MILP models for 8-bit ciphers.
Or any other SPN cipher.
So, and for any other SPN cipher. No, so I don't really understand, because for MILP model, it does not depend on the size of the S box, okay? Because we applied our MILP model for Skinny 128, which use 8-bit S box. So for this part, it does not matter. And for the CP model, it works for both the 4-bit and 8-bit S box. So, now, for the second part of the question, no, we didn't try any other block ciphers with this model. I know that some people are looking at AES with this model. But I don't know.
Okay, thank you. And I have a second question. You say you use the MIP model and you use the Queen-McCluskey algorithm to minimize the number of equations. So first, which MIP model do you use? MIP solver. And also, does the Queen-McCluskey algorithm actually involve some complexity gain? Or no, just sometimes gain?
Okay, so the question was about the use of Queen-McCluskey algorithm. And I don't remember the beginning of the question, but
The name of the MIP.
the name of the MIP solver. So we use the Gurobi for MILP solver. And okay, for the Queen-McCluskey algorithm, it was only to reduce the number of inequalities related to which table has to be added into the objective function. And actually, it only saved like two inequalities over 15 or something like that. So it's not a lot of improvement, but since we had to use it for a large number of fronts, I think it's still very interesting to use it.
Okay, thank you very much.
Probably very last very quick question from the remote attendees. No? Okay. So
Okay,
we can just thank Patrick again. Thank you very much. So what, did you send the slides? Okay. So just take 2 minutes to find the slides. Okay, so
Then
Also,
the
there we-
internet still sees it, right? Maybe stop sharing screen.
yeah, sorry.
Privacy sensitive.
Okay. So downloads, where downloads? This is your okay.
Sitting there still.
I think I will sit there because I listen. I will take it. All right. Sorry, so share screen. Sorry. So we should be able to use this.
Okay. Can I? Okay.
Okay. So the second paper that received the best paper award is about the cryptanalysis of low MC instances. And so congratulations for your paper. And Kashia will present this, I said right? Yes, the paper.
Thank you. Thank you for the introduction. Good
Excuse
morning,
me, you're still sharing the slides from the previous talk.
Oh, it's not sharing the screen.
Okay.
Resume share.
Stop share.
No, it's resume share.
No. Stop share. Okay.
Is it good now?
Yes.
Okay. So good morning, everyone. I'm Khashayar. Okay, the laser pointer, I don't think it's working. So I'm Khashayar from EPFL, and I'm here to present the joint work with Souedi Panik, Petul Durak, and Serge Rodenet called Cryptanalysis of Low MC Instances using Single Plaintext Ciphertext Pair. So, okay, first, let's motivate the problem and see why do we care about Single Plaintext Ciphertext cryptanalysis. So it all goes back to a post-quantum signature scheme called PICNIC. So low MC is used as a backbone scheme, as a backbone cipher in PICNIC. So PICNIC is a PQ signature scheme. It's a special variant of ZK-BOO. So ZK-BOO is a MPC and head paradigm type proof of identification that uses a transformation like Fiat Shamir or something. Yes.
I think you have 2 PDFs open because Zoom is still the first page.
Really? Okay. I don't see. Okay, can we check this? Here it's good for me.
Yeah, this is just first page. Or there is each delay.
I have no idea. Okay.
This is just your first page. Or
Yeah.
Can
So
you try the second one?
okay.
Do you see that?
No, I first page
Okay.
No, it's stop sharing. Stop sharing. You're
Yeah.
PDF open, I think.
Okay, where on the computer you mean?
Yes, now I see this.
Okay. I
Okay.
mean,
Interesting.
and what is yours? Yes, this
That's
right?
mine.
Now I see this side. Yes. Yes, perfect.
Okay. Okay, this is really laggy. Okay. So, okay, sorry for the thing that happened. Okay. So yes. So as I said, it's based on an MPC and head paradigm, and then currently is an alternate candidate in the third round of the NIST PQ standardization process. Okay, so let's see how the MPC and head paradigm works. So I took a help from my co-authors. So in an MPC and head paradigm, we have two parties. Let's say we have a prover and a verifier. And then my public key is going to be a ciphertext, a plain text, and a description of a cipher, you can think. And my secret key is going to be the encryption key that encrypts that plain text into that ciphertext. And me as the prover, I want to prove that I know that secret key. So what I will do, I will simulate an MPC computation on that cipher, and then commit to the computations that are done and send the commitments. Then the verifier will ask for some openings. I will open and he will check local consistencies. But okay, this is not very important, but the most important part is that my key consists of a single ciphertext and a plain text. So if I want to do a key recovery on Picnic by doing a key recovery on LowMC, I'm only given a single ciphertext and only one plain text. Okay? So, okay. As we know, whenever we say the word MPC, we don't like many multiplications because multiplications are very costly, which means that if E has many multiplications, then my whole signature scheme will be really slow. That's why in most of these paradigms, they use encryption schemes, they use block ciphers that have really low multiplication depth. And LowMC is specifically designed for that. So LowMC is a really simple SPN network proposed by Albrecht et al. It was designed specifically to be used for MPC computations on FHE. So it has a really simple S-box. It's a 3-bit to 3-bit S-box, which you can see it written there. It's a really simple quadratic function. And later, it's only followed by an affine layer and a key addition. And the good point is, okay, so the good point is the S-box is the only nonlinear part. So because both key schedule are linear, is a linear function, and also the affine layer, of course, as the name suggests, is linear. So the only nonlinear part comes from the S-box. And then it's just a minor detail that there is a additional key addition in the first round. Okay, so just let's set some notation. So whenever I say S, I would mean the number of S boxes that I have in round. N is going to be my block size, and R is going to be the number of rounds that I see. You can see the circuit on the right side, and you can notice that the domain of the S boxes are disjoint. So there is not a single wire that goes into two S boxes at the same time. And looking at that and knowing my S box is 3-bit to 3-bit, I can see that 3S should be less equal to N. And whenever it's equal, I will call it the full layer S box. And whenever it's less, I would call it a partial layer. Okay. So let's talk about some prior work that was done before this paper was published. There has been many other results after. So most famously, I think we can refer to Rechberger's attack from TOSC 2018, which also was optimized at Crypto 21 using some algebraic techniques. But these attacks don't really apply to the Picnic scenario. And the reason is that both are difference enumeration type attacks. And we don't have differences when we have only a single plain text and ciphertext. Okay. So as I said, these do not sit in the scenario that we have. So one might say, are we fine? Well, not quite. So let's talk about our attacks. So in this work, we propose two attacks. One is it's a linearization attack, and the other is a meet in the middle attack. Both of them are in the given ciphertext plaintext scenario and only use a single ciphertext plaintext pair. Both of them can break the full S-box variant up to 2 rounds, and the partial S-box variant up to 0.8 and over rest rounds. So the linearization attack is actually faster, although it's simpler. But the good thing is we were able to improve the meet in the middle attack in some work that we did after to break more rounds. Okay, and here you can see the complexities. For instance, if I have the full SBox variant with 129-bit blocks, the complexity of breaking it using the linearization is 2 to the power 91 encryptions, we can think. And also for the linearization, you can see that it's 2 to the power 109. Okay. Okay, so let's talk about the attacks. So let's have a closer view at how the LowMC SBox operates. LowMC SBox is written on the right, as you see. So as you can see, it's very sparse, and it's the only nonlinear part of the whole circuit. So the natural question is, can we linearize this SBox using just a few guesses? So an obvious way to do it is guessing 2 of the input bits. So if I guess A and B, for instance, then everything will be a linear function in C. But that's not very good. So the question is, can I guess 1 bit depending on the input of the SBox and linearize the SBox? And the answer is yes. So what we show is that for any guess of a quadratic balance function in the input bits, I can linearize the SBox. So let's do like a toy example to see how this works and take the most famous 3-bit balanced quadratic function that we know, which is the 3-bit majority function. Okay. So let's say I guess the majority, and the majority is M, the majority of the SBox inputs. So let's see what happens. So I'm going to look at the first output bit, which is A plus BC. The only nonlinear part in that is BC. And one can easily verify that if I compute 1 plus B plus C times M, I will exactly get BC. So if I guess M and I know what the value of M is, I have BC as a linear function of 1 plus B plus C, if M is known to be a constant. So yes, I can write my output bits using the majority guess as linear functions in A, B, and C, if the majority guess is known. Okay, now mounting the attack after knowing this is pretty natural. So okay, first let's talk about the general case of this result. So simply, this is the full theorem that we have, that we say for every balanced quadratic Boolean function that we guess in the input bits, I can write my SBox in the following form, which simply is that I can linearize it in a way, knowing the majority, knowing the value of F for the input. Okay, so let's see how the attack works. So the attack is really simple. The idea is for every single round that I have on my cipher, I will guess the input majority of all the SBoxes that I have and linearize all the SBoxes. And then I would get a linear equation of form a linear dependency on PT and K is equal to my ciphertext. So let's see how I can actually compute this equation. So let's take one round. I call the input to be I, let's say. Knowing the majority guesses, I can write the output of the SBoxes as a linear function in I. The affine layer is not doing anything much. It's just like adding one more, multiplying one more affine matrix to the value that I had before. And then the key schedule is also linear. So I get something in the end of the round that is linear in the inputs and the keys. Okay. So doing this for every round, I can get that type of equation that I want. And what happens after? I just solve this equation for K. But after I solve this, I should make sure that the majority guesses that I did were actually legit. So the key that I guessed is actually consistent with the majority guesses. So I need to check the consistencies by doing one more encryption, simply. Okay, so let's check the complexity of this attack. I have 2 to the power RS possible majority. So R is the rounds, S is the number of SBoxes in each round. So for each majority guess, I have to create this linear equations. I have to solve the linear system, and I have to check whether K is consistent with the majority guess. Okay, the first one is n encryptions, approximately. The second one is 1 Gaussian elimination, or as we have an argument, it's n over 2r encryptions. And the last one is just 1 encryption. So that's my total complexity. And because I have that 2 to the power RS term there, if I go to 3 rounds and in the full SBox setting for a full layer SBox that my S is n over 3, then the best I can do is break up to 2 rounds of my full layer variant and to 0.8 n over s rounds for my partial layer variant. Okay. So let's go to the meet in the middle attack. So the idea here is I will linearize everything other than the first round. So I will keep my first round as is and linearize everything that comes after. Then I will be splitting my k into 2 parts, k1 and k2, and then try to form some equations such that the left-hand side would only depend on k1 and the right-hand side would only depend on k2. And having this, I can, because k1 and k2 are like almost, we can think of them as half the size, I can try to do like a meet in the middle type of attack, like try to find collision for these pairs. Okay, so let's see how I can form the equations. So the idea is I will look at the state that is the output of the first round and the input to the rest of the rounds. Okay, so let's look at the backward direction because we have linearized all the rest of the rounds. So exactly, I will write my k1 to be first half of the key, my k2 to be second half of the key, and then w to be that middle round. So I will guess the majority of the S boxes for the input majority of the S boxes for all the rounds other than the first one. And then I will linearize all those rounds and get this type of an equation, just as I had before. So I have a linear equation in K, and CT is equal to W. This is exactly what we had in the linearization case. And now, because I can write my K to be K1 plus K2, and L is a linear function, I can get an equation of this form. So W is a linear function in K1, plus a linear function in K2, plus some constant t. Okay? And now let's see how the other direction works. This is also very easy. So what I will do is that I will propagate my circuit in a forward direction and try to get a quadratic equation of that form. And one might ask, why can I get that? Because I have those, my functions are not linear anymore because my S boxes are quadratic. But the point is, if I take K1 and K2 such that their lengths are divisible by 3, no bits from K1 and K2 will pass through the same S box. So everything will still be separate from each other. Okay. So I can write exactly an equation of that form. So some quadratic f of K1 plus some quadratic g of K2 plus c is going to give me exactly the same W. And now I'll just have to combine the two together, and I get an equation of this form, which f and g are quadratic, and a and k are linear. And from here, it's pretty obvious what should be done. So we just have to do a collision search for K1 and K2 on these values. So I will just compute f plus a plus c for all K1 values that I have. Then I will compute g plus b plus d for all K2 values that I have. Keep 2 lists of these, and then find the collision between the lists. Okay. Okay. So let's check the complexity. So let's see what do I need for each majority guess. I have to form these quadratic equations. And then I have to evaluate f plus a and g plus b on those smaller spaces that I had. And these we also can optimize it using Trezor. So I have 2 to the power r minus 1 s majority guesses. And forming equations is not really costly compared to the next part, which is going to be approximately 2 to the power n over 2 encryptions. Okay. And I can get rid of a factor of square root of n over 2 using Trezor there. Okay. And this is going to be my total complexity, which again allows me to break up to 2 rounds of the full S box variant. Okay. So I'm going to quickly go over to how we can do a meet in the middle for the partial layer S box. It's a bit of a different scenario, and then conclude the talk. So, okay, here again, I want to split my key into K1 and K2. But here the point is, I kind of cannot do the same because I have many more rounds and my degrees will start to get really high. So what I will do, I will have K1 and K2 to be the round keys that were used in like some rounds in the beginning and some rounds in the end. So the idea is I will split my rounds into 3 parts. So I have R1 rounds in the beginning, as you can see on the right. I have R2 rounds in the middle and R3 rounds in the end. So for the rounds in the middle, I will again guess the input majorities for all the S boxes that I have, and I will linearize them completely. And then I would do something similar for the first and last rounds that I have similar to what I did for the full SBox layer. Okay. And so I will call K1 to be the keys that were used in the R1 rounds and K2 to be the keys that were used in the R3 rounds, and then try to do some kind of a meet in the middle for K1 and K2. But the good thing is, I can actually argue that I can consider K1 and K2 to be of short length. And why is that? That's actually an argument that was done in Rechberger's attack from 2018. The fact is that although I have these really, I hope the pointer is visible, although I have these really key additions that are being done here, as long as a key bit is not passing through an SBox, I can just apply the affine function and push that key to the next round. And I just keep doing this and push that portions of the key to the last round, for instance, and just have smaller keys for each round, which are the size of the input bits of the SBox. So for each round, the length of my key is the size of the inputs of the SBox. Okay, so what I will do is that for the first R1 rounds that I have, I will push all these keys forward. So for all these R1 rounds, I will have really small keys. And also I can do this in the backward direction. So I will do this in the backward direction for the R3 rounds somehow. So K1 and K3 now will have only 3s R1 and 3s R3 bits, because that big key is now in those middle rounds that I was linearizing. Okay. So now let's see how the attack works. So I will I will denote the output of the R1 rounds as W, output of the input of the R3 rounds as V. And now because those middle rounds are linearized, W and V have like a linear relation between them. We will see in a bit. But most importantly, I can write my W as a quadratic function. I can write it as a quadratic function in K1. And I can write my V as a quadratic function in K2. And then V can be written as a linear function in W, K1, and K2 because I've linearized those rounds. And again, I derive to an equation of this form. So, okay, yeah, it's just one slide. Okay. So I get that L plus Q in K1 is equal to L prime plus Q prime in K2. And then again, I do a meet in the middle because I have this type of an equation. Okay, and then so there's written that R1 and R2 should be approximately n/6 for the attack to work. Okay, so let's conclude this talk. So we proposed two attacks. The first one was a linearization attack. It breaks up to 2 rounds for the full SBox variant and 0.8 n/s rounds for the partial SBox variant. You can see the complexities there. We also have a meet in the middle attack that breaks up to 2 rounds for the full SBox variant and 0.8 n/s rounds for the partial SBox variant. The bad thing is it's slower. The good thing is actually it can be combined with another meet in the middle that we do in a work after this and can break more rounds of low MC as well. Okay. And okay. And thanks for listening. And the takeaway message is be careful when you plan a picnic. Thanks a lot. Oh, okay. Yes. I forgot.
So thanks a lot. Are there any questions? Are there any, Bart, are there any remote questions? Okay, there's a question from Christine.
Hey, thanks for the nice work. Could you briefly comment on the memory cost of
so the memory is not very nice because you have to keep those very long lists. So I can think that you need like 2 to the power n/2 somehow memory to do it. But okay, we have like some work that we're actually doing now. It's not available yet, but exactly we address the memory issue, how we can optimize it. But yeah, it's not really memory efficient for sure. Yes.
Thanks.
Are there any other questions from the audience? Okay, so
okay.
Thank you very much.
Thank you.
And we can move to the next talk.
to go through this one. No need to repeat it.
It's ready for screen, yes. So yeah, I will just do the introduction. So next paper, so also a best paper award. It's on wikis and reduced ages and Tiagosin. So Willie Mayer will present this paper. So congratulations for the best paper award. And so I'll let you, present the paper.
So this is joint work with Fukang Liu, Takanori Isobe, and Kosei Sakamoto. Normally, Fukang would give the talk, and actually these are his slides. So a brief overview. So I would like to talk about cryptanalysis of ages mainly. First, I give a description of this cipher, and then the attacks, and very briefly I also talk about cryptanalysis of Jiaxin, and then I come to a summary with a brief discussion and conclusions. So some background on ages 128. Ages 128 belongs to the ages family. So there are different variants. So depending on the key size and also some other kind of issues, this family has been designed by Wu and Prenel and has been submitted to the CSER competition. Actually, ages has been selected in the final portfolio of the high performance applications in the CSER competition for authenticated encryption. So we find that ages is still a novel and efficient design that uses the AES round function as the main component. There is something surprising here. There seems to be no cryptanalysis of the ages initialization phase thus far, despite the quite long history of the CSER competition. There are actually two very interesting papers for the keystream phase, but nothing on initialization. So we are really wondering whether it's too difficult or just not interesting, but we find it interesting because it's a dedicated AES-based cipher. So it's non-trivial to find out its security, especially regarding initialization. So a brief description of ages 128 initialization. As we can see, we have 5 blocks or words. Everything you can see here is 128-bit long. And A is just an abbreviation for one round of AES, where we omit constant or key addition. The key is introduced in the first part here. So actually, it's depending on the parity of the round number. It's either K XOR N or K. So if R is odd, so it's shown here. XR0 is XR0 minus 1 plus AK, A of XR minus 1, 4 plus K. And the other words are updated in a similar way. So if R is even, also the nonce comes in. So we have a nonce of 128-bit, as is quite common for this type of ciphers. So the total number of rounds is 10, and the initial state, we can see that only X0 depends on the nonce. X1 and X2 are constant. X3 depends on the K, and X4 also depends on the K. The output after R initialization rounds is assumed to be visible to an opponent, which is theta is XR1, XOR XR4, XOR XR2, and XR3. So there are quite some deviations actually from AES, despite using it the round as a component. Therefore, we have been looking at what is known about AES. A lot is known. There are really many papers. of course, there is a well-known 4-round integral distinguisher. There is even a 5-round multiple of 8 distinguisher. And a bit more recently, there are the 4, 5 or 6-round yo-yo or yo-yo-like distinguishers. So which of these distinguishers could be applied to the AGES 128 initialization? And we recall the observable output, theta, and we thought that the integral distinguisher is more suitable because we can independently study the integral property of each of these blocks or words, and also of this AND operation. We guess that the other attacks may require to study possible interactions between words, but we don't say that other kind of known results wouldn't apply. So our main strategy is to write down and study the integral properties of the expressions after R rounds, independence of the nonce and the secret key K. One wonders whether one would also look at Boolean expressions, maybe like cube attacks or something like that. But we thought that the expressions are really complicated, and also the state is very large as you compare to maybe cube attacks on stream ciphers with small state or something like that. So we are looking at expressions in terms of the 128-bit words as a unit, because the diffusion between words is not that strong if you look at the definition of AGES and its initialization. So actually it's an exercise to write down the expressions in terms of n after 5 rounds. So, well, if you consider this, well, is it nice? Or actually, I should explain these red A's. If one would write down step by step, we have noticed where the new terms come in after iterating one more round. So this A means that comes in the last step from the 4th to the 5th round. But still, it doesn't look very promising. So what can we do here? And also we have this nonlinear part x5, 2, and x3. So we need to do something better. So we recall the initial state. So we have this, what we have seen before. And then we write down for each round the expressions. So of course, what we can do, everything which is constant, we just abbreviate with another constant. We have already the constants C0 and C1, and then we just count up for new constants. So if R is 2, we have other things which are constant. And so this is the expression. That doesn't look very complicated. We needn't to look at the details. We just, at the moment, it suffices if we look a little bit at the global picture. If R is 3, it's even already a bit more complicated. But an interesting thing is that the underlined expression can be simplified by adding a condition on the key. So, and this is a crucial condition now. If A of K plus C1 of the diagonal part. So I should explain this notation. We have the state after applying A, and we just look at the main diagonal. And if this coincides with the main diagonal of K, of course, we should say that we represent 128-bit word as we do in AES as a 4 times 4 bit array where each entry is 16-bit. And in this language, this expression 1 does make sense. So if we assume this condition, then this whole underlined expression we have seen here becomes constant. Of course, these are just claims here in this talk. These are all based, I should say, on at least 5 properties which we had proved. First, well, when you verify these things, they look quite easy, I would say. But first, it was not so trivial to find out these proper properties. So we can introduce a new constant. And then after 3 rounds, things look not so bad. So it's okay for doing some further analysis. But we have to do some other things. So we have further introduce another variable t, which is C0 XOR A of k plus n. Then X3 looks quite simple. So that's really, really simple. So why is it useful to introduce still another variable? So as we see, it makes all our expressions simpler and maybe easier to study. Another trick is we can get one more round in a kind of non-trivial way. Actually, remember that for block ciphers, maybe we can just add 1 or more rounds by partial key guessing or whatever. This is not the case here. We have to do something quite dedicated. So often we now study t rather than n, but also that is not quite trivial because we have to swap between t and n. N is visible, but t is not, is only implicit. So if we go for 4 rounds, then we have this expression here. So I skip it. But for 5 rounds, it still doesn't look very, very promising. So even after only 2 more rounds, we have some relatively complicated expression. And we wonder whether we are capable of now applying an integral distinguisher. So we focus on each word separately. So X51 is the simplest. It has this form. And we can actually prove when we sum over 2 to the 8 values to t of 0, 0, then this sum is 0. So this is an integral property. And actually, it's not detailed here, but it depends heavily on the definition of t and its properties and how going from n to t back and forth. So second, we focus on X54. So this is still quite complicated. The first summand, a of t plus something, that it's not so difficult. We can derive an integral property based on the well-known 3-round AES integral property. But how about the second, more involved, summand? So if you look in it in form of a picture, it doesn't look very promising. So first we have A for all, C for constant, and then but further, after 3 rounds, it seems we might lose track. So we look at it in more detail. We consider the function g. G is actually the function that's the argument of the latest A here, of the leftmost A. And then it was proved in the paper, again, if T00 takes all possible 2 to the 8 values for each I and j, the same value of g, I, j will appear an even number of times. So we have finally, after the XOR, we have even, and after applying another round, we have still balanced. So we have still an integral property, which is expressed in the lower bound equation here on the side below. So finally, we need to focus on the AND part. So the A of t, that's okay, but then we have the all underlined stuff, and it suffices to look at the sum of A of t and A of t plus c. where we sum again over all 2 to the 8 possible values of t00. So we could prove that it has indeed an integral property, but only if we restrict on the columns of the state 1 and 3, but we ignore column 0. So this is again illustrated by a picture here. Actually, it's equivalent, the formula and the picture. Therefore, for 5 round ages, we have this nice integral property, and we could even derive an ordinary integral property using the definition of t, so that when we sum over the full diagonal of n of the nonce, then the sum over the values of theta is still 0. So we get an ordinary distinguisher. Then we have the weak key condition. Actually, in order to go back and forth between t and n, we need to introduce a weak key condition. And we look at this. There are 2 to the 24 possible values for the diagonal imposing this condition. And this can be pre-computed in a table. So we first studied, because we can, weak keys can back and forth, we can study the distinguisher in terms of t rather than n, and using the relation t, the definition of t, and we can recover the value of the full diagonal of k. So we again need the weak key condition, and it's going rather step by step. That's ignored here. Actually, it's a bit more complicated than what is given on this formula, but it ends up with a key recovery attack with theta complexity 2 to the 32 and time complexity 2 to the 72. And the number of weak keys, because we have imposed a condition of 32 bits. So this means we have 2 to the 96 weak keys. We obtain a valid key recovery attack because the complexity 2 to the 72 is quite lower than 2 to the 96. Actually, there would be 4 classes of weak keys. Instead of the main diagonal, we could also use the other 3 diagonals. So a very brief comment on Jiaxin. So we applied similar ideas, but the technical issues are a little bit different. Especially one special thing is that we have to impose conditions on the constants, which is rather uncommon. So actually, our attack only works if one would choose weak constants. But fortunately, the constants chosen in Jiaxin don't fulfill these conditions. So I skip this part and come to the discussions and conclusions. So maybe studying ages and Jiaxin-like ciphers, we have to impose weak key conditions. Otherwise, we didn't succeed in any attack. But still, in this setting, we reach half the number of initialization rounds. Maybe one could say, well, it's not very exciting. On the other hand, it's quite, we think it's, nobody has done it before, and I find it's non-trivial. So for Jiaxin, there seems another issue that actually one round is kind of useless because we can skip it to some extent. So what we can say finally is that this is a rather dedicated analysis. So it does not follow immediately from known results on AES. So therefore we thought that it's an interesting contribution, and maybe there could be other kind of analysis of similar ciphers. So thank you.
Thanks a lot, Will. Are there any questions? Are there any questions from?
No, but I have one question actually. So that you have three constants. You actually need them for your attack to work, right?
Yes.
Is it due to the scheme or is it due to your attack? Do you think you can extend the
A
attack?
very good question. Actually, it's quite open because it's.
Please
now-
repeat the question.
Yes, whether this restriction on constants, whether it's due to our attack or due to the scheme, due to the design. So actually, I cannot really finally answer this question because our attack is rather dedicated and maybe somebody else could come up with another attack. Actually, we also tried some divisibility properties. Maybe there is something, but our conclusion was that the basic divisibility property methods wouldn't work. But maybe there is some follow-up work which can break more rounds or resolve this relevant question for Daoxin.
Are there any other questions? I have a very short one. I did not understand. You said for Daoxin there is one round that is kind of useless. Is this for this attack or in general for all kind of attacks?
That's again very interesting because if somebody else would like to do another design, so definitely you should check our work and of course try to see whether other kind of similar attacks might work.
Thank you. Thanks a lot. So this is the end of the session, so we can thank again all the speakers. And now we have a coffee break of half an hour. Yes, so we can stop and come back. So people that are presenting the next session physically, please find the session chair and come here to put your slides on before